Good morning, students. So in the last class, we discussed the very important phenomena in quantum mechanics, which is nothing but quantum tunneling. The penetration, the wave function penetrates into the barrier. So that is very important phenomena, which this phenomena will never occur in all these subjects except in quantum mechanics. So we applied those tunneling effect few applications, and we discussed about scanning tunneling microscope, tunnel diodes, and very important thing is alpha decay, alpha emission. And alpha emission is nothing but it's a spontaneous radioactive decay process in all the radioactivity elements, especially if the mass number is greater than that of 210 especially. So very large, very big nucleus that will emit spontaneously the alpha particles. So alpha particles nothing but helium particles. They are all unstable. Suppose when you take very small size of nucleus, so it's very around say 50 or 100, it's a very small amount. Then those elements will be stable and it will never decay. It will never undergo decay process. So they are all stable. There are actually two forces exist. One force is nuclear force, which is very strong force in the nucleus that binds the nucleons. So it's an attractive force. Then another force, which is a Coulombic force, which exists among the protons. So there is a competition between these two. For small nucleus, the nuclear force will be dominant, which binds the nucleons. So it will be dominant. So the elements are stable. It will never undergo decay process. Whereas when the nucleus is very large, the size becomes very larger. The radius or distance between that also will become very larger. And it so happens that the Coulombic force, that is the force among the protons, will dominate. Then the nuclear force. Then slowly alpha emission will take place. So there is a competition between these two. The Coulombic force now will dominate and nuclear force will be suppressed. So this process is nothing but the unstable process, and the element will undergo radioactive elements will undergo radioactive process. That is alpha particle will be emitted. So this is called alpha decay or alpha emission. So alpha particle will be emitted. So alpha particle is nothing but a helium nucleus. And in this class, we are going to discuss the main example for quantum tunneling, how it has been applied in experimental side, especially George Gamow. George Gamow, who applied this theory in the year 1928 after the discovery of Schrodinger wave equation, especially four problems, that is Schrodinger time dependent, time independent, and quantum tunneling well problems. So he put forth his idea into the theoretical side. He explained, and also he related this idea into Geiger-Nuttall formula, which we are going to discuss now. So there are three things we are going to learn. One is quantum tunneling, the example of quantum tunneling, which is nothing but the alpha emission, and second one is how Gamow applied this theory to explain the alpha emission, and third one is Geiger-Nuttall formula, which is related to alpha emission. And 30 years it was not solved. It had not been solved for 30 years, nearly 20 to 30 years. The moment when the explanation came from Schrodinger, especially tunneling effect, people used this idea into this process and the equation has been solved. Okay, Geiger-Nuttall equation. So which we are going to see now. So alpha decay is the process in which a nucleus loses an alpha particle and is converted into another nucleus. Okay, so big nucleus that will convert into another nucleus by emitting alpha particle. So with the charge number less by 2 and mass number less by 4. So in almost the mass number and the charge number it will be reduced, and the remaining then we will obtain as a helium particle. So this is nothing but alpha particle. So as I said, the large subnucleus, generally A is greater than 210, spontaneously will undergo emitting alpha particle and decay process, which leads to the emission of alpha particle. So they are unstable. So before emission, an alpha particle is assumed to exist inside the nucleus. We know already. Before emission, we just consider nucleons are inside the nucleus. So alpha particles are held inside the nucleus by strong attractive short range forces. So they are all short range forces, nuclear forces. We will see in detail about in the figure. However, they are outside the nucleus. There exists a strong Coulomb force. As I said, if A is greater than 210, there will be a strong Coulombic force among protons. So there will be a repulsive force. So nuclear force will be attractive force. So if A is greater than 210, the Coulombic force will dominate than the nuclear force. If it is less, the nuclear force will dominate the Coulombic force. So this is a competition between these two. So however they are outside the nucleus, there is a strong Coulomb repulsive force between the residual nucleus and the alpha particle because of both are positively charged. So all protons are positively charged, so there will be a repulsive force. So it's nothing but a Coulombic force. So nuclear force is the strongest force, we know already. It dominates the Coulomb force in the smaller sizes of the nucleus. That's why they are stable. As the size increases, the distance between the nucleons increases, the Coulomb force starts dominating now and it becomes unstable. When different kinds of decay process for different kind of nuclei have been studied, and it's found that the maximum kinetic energy of the alpha particle ranges between 4 and 10 mega electron volt. Okay, so the range of alpha particle, the kinetic energy lies between this range 4 to 10 mega electron volt, 10 power 6 electron volt. Okay, now we will look into the picture. It is nothing but the nucleus potential graph, the variation of potential, nucleus potential with alpha particle distance from the center. Now we just look at this picture. Now we know that nucleons are confined in a particular region, and of course it's a periodic potential. Now we are going to approximate this periodic potential in the square potential value. So this is a square potential value. So it's nothing but a nucleus. We are going to approximate. So this is just an approximation where nucleons are held up inside the potential. So where nuclear force exists. Okay, and Coulombic force also exists. Now in such a way that if the case is A is greater than 210, so they are all unstable, just now we discussed, correct? So what happens, and the Coulombic force will dominate. So this is nothing but a Coulombic force. So this is a graph is nothing but minus E squared by 4 pi epsilon naught R. Okay, minus 1 by R. So this is the Coulomb force. The nucleons are confined in this within the nucleus. This is the model which we have assumed that this is a square potential well. Suppose if we consider the kinetic energy of the alpha particle, which is nothing but 4 to 10 mega electron volt. Suppose if we consider, and this is the height of the barrier. For certain nuclear reactions, we had the height which is nothing but 27.8 mega electron volt. If we consider the height for certain nuclear reactions, the height is nothing but 27.8 mega electron volt. So this is the height. And what is the kinetic energy of the alpha particle, which is less than that of the barrier height? But it is found that few alpha particles, they will penetrate into the barrier and come outside the barrier. Even though height is look at the height, it is 27.8 mega electron volt. The kinetic energy of the alpha particle is very less. It's around 10 mega electron volt. So it cannot escape. So we have to give classically, just if we talk classically, we have to give enormous energy. We have to give more than 27.8 mega electron volt, only then we can cross the barrier. Whereas in quantum mechanics says that there is a chance of these particles, they will penetrate into the barrier. The height is more than that into the barrier, and it will leak out, it will penetrate. Okay, what does it mean? It means that the particles are associated with the waves. So we know already particles are associated with the waves in quantum mechanics. These waves, even though the barrier height is very larger, the kinetic energy is smaller, there is a chance that it will penetrate into the barrier. So this is a barrier. See, this is the barrier. So this is the barrier. From right from the beginning, these are all barriers. Okay, so this is a barrier. So, and of course, it depends on the width. width of the barrier. Okay, it depends on the width of the barrier. We will see later. Okay, so this is the idea. Because the kinetic energy of the alpha particle is very less, because it's associated with the particle, there is a chance of passing through the barrier, though the potential barrier height is very large. So this is the idea behind. Okay. Classically, the particle is confined to the nucleus because of the high energy requirement to escape very strong. Just now we said nuclear potential well. Also, classically, it takes an enormous amount of energy to pull apart the nucleus, and even that would not occur spontaneously. Whereas in quantum mechanics, just in the opposite nature. However, there is a probability that a particle can tunnel through tunneling effect, which we have taken from the previous lecture. So, tunnel through the wall of the potential well, and it can escape through the barrier. Classical mechanics cannot explain how a particle of energy ranging from 4 megaelectron volt to 10 megaelectron volt can come out of potential barrier height of 27.8 megaelectron volt. So in 1928, George Gamow solved this puzzle by using wave mechanical consideration. So immediately after the Schrodinger's wave equation, so discovery of Schrodinger equation, he used Schrodinger equation, tunneling property and all those things. He used this one and he solved this kind of alpha emission from the nucleus. His theory is based on quantum mechanics formed by combining de Broglie hypothesis and Schrodinger equation. Gamow solved the model potential for the nucleus and derived from first principles a relationship between half-life decay, which we will see later, event, and the energy of the emission, which had been previously discovered empirically. So it was discovered earlier by Geiger-Nuttall law, 1911. That's why I said right from 1911 to 1928. So it could not be solved for longer period. People have found out the law. This is the empirical law. Empirical means out of experimental we can get some law, we can get some graph. So that's called the empirical law. Just pure experiment. Okay, this is an empirical law. So Geiger-Nuttall law, it started in the 1911, but it could not be explained up to 1928. So over 26-27 years. Okay, so an alpha particle is associated with a wave which has a wave function that has certain probabilities of penetrating into the barrier. Even the particle has kinetic energy less than the barrier height. So this is called quantum tunneling. And the tunneling probability is given by, so we studied under the tunneling property is given by this expression. So in the last class. And T is, just look at T, mainly depends on the width of the barrier. So T depends on width of the barrier. The width of the barrier is very small, very small. Suppose the tunneling probability is very high. If the width is very large, tunneling will be small. So this is what we studied in the last class. So T directly proportional to e to the power minus 2k2m. So k2 is given by this. So of course the transition probability is related with the width of the well. Okay, barrier width. It's a very important thing. Higher and barrier and wider it is, the less chance that the particle can get through the barrier. So this is what we discussed. So now we will have the analysis of Geiger-Nuttall law. So this is what we discussed. This is the potential well for the nucleus, which we discussed in the just now. So now we will take three energies. Okay, for example, we will take first energy E1 and second energy E2 and third energy E3. Okay, we are going to consider. For all the three cases, we are going to discuss the transition probabilities. And these transition probabilities are associated with the lifetime, half lifetime. So we are going to discuss all the three. So first energy E1. So E1 has the width from here to C. Okay, this is the width, effective width, potential width. E2 has the width B and E3 has the width A. So this is your Coulomb attraction curve. Okay, so where it leaks out it implies that this is the effective width. So this is your effective width. This is your effective width. See, E1 we have taken already three energies. E1, the kinetic energy of the first particle E1 is lesser than that of E2, than that of E3. Now you just consider all three cases, in which case the particle will go penetrate very faster? In which case? You just consider, because effectivity is very small. So E3 will go faster. The transition probability will be very strong. It will go immediately, it will go outside. Okay, but here effectivity is very larger, greater. So it will take lot of time to go through. So the kinetic energy is very less, but the transition probability also will be very less. So this is what is given. Consider 3 alpha particles having energies E3 is greater than E2, E1. The transition probability for E3 will be greater. It will go immediately to E. So, and also we can find that the kinetic energy is very less. The transition probability also will be very less. As I said, this is closely connected with the half-life period. The mean lifetime of the nucleus is just reciprocal of the transition probability. Okay, just reciprocal. That means the half-life of E3, higher energy, will be very less. Very less. It has to stay for a longer time to go outside. Okay, the half-life of E1 particle having very less energy will be greater. Okay, it implies that short-lived alpha particles have greater kinetic energy and long-lived alpha particles have lesser kinetic energy. So this is related with Geiger-Nuttall. Okay, Geiger-Nuttall in the year 1911. So relation. This is a Geiger-Nuttall relation. This is a straight line relation. This relation has been obtained from experimental data. They could not explain. So at the time the tunneling was not found. So 1927, after 97, they started explaining clearly. Okay. So they explained that we have a relation like this and we have the formula exactly like this. And this is related with the half-life period and kinetic energy, which we discussed just now. Okay. So kinetic energy, half-life period. So it's clearly, it says that this is proportional to the square root of the kinetic energy of the alpha particle emitted. Okay, square root of the, so square root of the alpha particle, this is root of kinetic energy is nothing but kinetic energy of the alpha particle. So which we have drawn between x-axis kinetic energy, Z by kinetic energy, and y-axis the half-life period. Okay, so this experimental data clearly explains the quantum tunneling, and after that people started doing lot of experiments. So where A and B are out of this relation, A and B are constant, and this equation 2.102 is known as Geiger-Nuttall law, and this alpha decay can be explained by barrier penetration phenomena, especially quantum tunneling effect. So this is about alpha emission. Okay, now we are going to come to the next session, Bloch waves in a periodic potential. So far we discussed 3 models. One is infinite quantum well, finite quantum well, and barrier potential problem. In all the 3 problems, we considered the potential is constant. Correct? Where V0 is constant, V0 equal to 0 or V0 equal to the maximum value, constant. Correct? In all the 3 cases, we have considered 2 ideas. One is the potential is 0, then another one is potential is constant. But actually speaking, the electrons will undergo in a lattice, in the crystal, periodically. The periodic potential exists. So varying potential exists. So electrons will go in a crystal from one atom to one ion to another ion periodically with a variation of potential. It is not constant potential. This is reality. So periodically it moves. It implies that some plane waves will be associated along with the periodicity. If you multiply the periodicity depends on the periodic of the lattice. Okay, this periodicity with the plane wave equation, that will be the complete solution which was given by Bloch, Felix Bloch. So he is Felix Bloch. So Felix Bloch he was a Jew. He was born in Switzerland in the year 1905. He had an elder sister, and when he was 3 years old, his elder sister passed away. He was so upset and almost depressed. Again he came out, and his dad, Gustav Bloch, his dad's name was Gustav Bloch, and he was a wholesale grain. They were conducting some grocery shops, and he attended some classes in the school. Then he graduated went to the college and he met Peter Debye. Debye's temperature probably we know. So Peter Debye was an inspiring guy for him, and he learned all his physics from Schrodinger, Peter Debye, nearby professors. Then Peter Debye inspired him to go to German and meet some scientists. So immediately he went to German. He met Heisenberg. So Heisenberg's first PhD student is Bloch. So he was first graduate student. So he went to Germany and he did his PhD work under Werner Heisenberg. Quantum, this is about, the title goes like this: Quantum Theory of Solids. This is about the periodicity, the behavior of electrons in the moment in the crystal. So this was his PhD thesis. Then after that he did lot of works on quantum mechanics, especially ferromagnetism, spin waves, Bloch waves, Bloch spectrum, Bloch sphere, so Bloch spin, so some radioactive elements also. So lot of things he did. In the year 1952 he got Nobel Prize. He got Nobel Prize along with Purcell. So he went to US because 1933 he was a Jew, as I said. So he went to US in those years, 1933-34. Then he became a citizen of US and he participated in many atomic bomb discussions and all. In fact, he became the first director in CERN, CERN. It's a very famous nuclear observation under UK. And from there he was a pioneer person to start discussing about the atom bomb. So very famous person, Bloch. He got Nobel Prize in 1952, in the year 1952, and he shared the Nobel Prize with Purcell. Purcell also, they got about radioactive functions, inductions. Okay, so he is Bloch. Okay, we are going to discuss. So the idea is, as I said, you have the wave function. This wave function, which is equal to, it's only one idea. Okay, wave function is equal to periodicity multiplied by plane wave. So periodicity multiplied by plane wave is a Bloch wave. Periodicity multiplied by the plane wave, Bloch wave. Bloch waves will exist in crystals. So this is the idea. Earlier Sommerfeld put forth quantum theory of solids. That is, the electrons will move in a constant potential. So this was the idea given by Sommerfeld. Whereas Bloch said on the other way around. Bloch said the electrons will go in a periodic manner. With constant potential, it is periodic potential, and using periodic waves. So this is the idea. Okay. So in metals, there are many atoms, they are periodically arranged. We know that already. Okay, forming a lattice with a lattice constant A. So your periodicity is connected with lattice constant A. The distance between two lattice points is nothing but A. We consider conduction electrons in the presence of a periodic potential due to Coulomb potential of positive ions. The electrons undergo movements under the periodic potential as shown in figure 2.11. Okay. So of course we know, we discussed earlier this graph earlier. So these are all lattice points in which nucleus exists, and this is about the movement of the electron. So electron dispersion curve. Okay. So V equals minus E squared by 4 pi epsilon naught R. This relation is minus 1 by R. So that's why graph like this. Okay. At R equal to 0, you have infinity. V is infinity. Okay. And in between these two, your potential energy will be minimum. Here potential energy is maximum. So this is something like that. But it is in a reverse way. V equals minus. Correct? Minus. Okay. So I want to say that this is potential energy is maximum, potential energy is minimum, because infinity. V is directly proportional to minus. Okay. So the electrons undergo movements under the periodic potential. Such electrons called Bloch electrons. Okay. The Schrodinger equation at points x. For example, if you consider this is x and you are going to consider this will be x plus a. We are going to consider this as x and this must be x plus a. X plus a goes on because a is a periodicity. So Schrodinger equation is given by, in the first at x equal to, at x point it is given by this expression. Okay. Similarly at x equal to x plus a. So x becomes x plus a. The same thing, x becomes x plus a. Okay. So about Felix Bloch, the behavior of electrons in the periodic potential is studied. The Bloch wave is a type of wave function for a particle in a periodically repeating environment, as I said, repeated. A one-dimensional metal crystal consists of a number of positive ions, as I said, nucleus, positive ions, with a periodic potential is considered. Just now we have seen the figure 2.11. Then according to Bloch theorem, the periodic potential form of electron wave function is given by this, V of x plus Na. N is a periodicity number. So V of x plus Na is nothing but V of x. So that's why we have written V of x on both sides here. See, it is not x plus a. V of x plus a equal to V of x. Okay, according to this. So where a is the periodic lattice constant and V of x is the periodicity of the lattice, as shown in figure 2.11. So it has to obey this relation. V of x equals minus e squared by 4 pi epsilon naught x. Okay. Now we are going to see in detail. In metals, there are many atoms. They are periodically arranged forming a lattice with a lattice constant A that we know already. So it's repeated, it seems. Okay. Such electrons are called Bloch electrons. Now we will see figure 2.12. So as I said just now, that your wave function is nothing but the periodicity multiplied by the plane wave equation. So this is what the figure goes like this. Okay. So you have see every atom is arranged periodically. Okay. The electrons, the movement of electrons which are associated with the wave packets, so they are like this. A complete wave is nothing but the result that will be your L, and your psi of x will be psi of x plus L, and of course L equals Na. N is number of unit cells. Okay, there are lattice points, so there must be unit cell. Is it okay? Now the Schrodinger equation at points x and x plus a is given by this expression we know already, and this is what I said. The wave function is nothing but periodicity multiplied by the plane wave equation. Okay, periodicity multiplied by the plane wave equation. And here u of x is nothing but it has to obey periodicity. So u of x plus a equal to u of x. Okay. So you substitute now. You substitute in this expression. Psi of x equal to e power I x u of x. So your psi of x plus a becomes e power I. Instead of x you will have to write x plus a. Instead of x you will have to write x plus a. You just separate. So this will give you e power I k a, e power I k x u of x, because u of x plus a is nothing but u of x. So this can be written as e power I k a. The total thing can be written as psi of x. Since psi of x and psi of x plus a satisfy the same equation, psi of x also same equation. Okay, satisfy the same equation. They differ only by the multiplicative factor e power I k a. That is e power I k x. So only they differ only with the multiplicative factor e power I k a. So we can write multiplicative factor as psi of x plus a equal to alpha psi of x. So we are going to consider this multiplicative factor as alpha. So for number of unit cells, so alpha will become alpha to the power 1 become alpha to the power n. So this will be replaced by Na. A is replaced by Na. Okay. So that will form a total ring. So it is exactly connected with the total ring. So psi of x plus Na becomes a to the power n psi of x. That's total ring is nothing but totally we can collect this as psi of x. If it is so, then alpha to the power n must be equal to 1. If it is so. Okay. The 1 can be written as e power 2 pi in. This 1 can be replaced. 1 can be replaced with e power 2 pi in. Suppose you substitute n equal to 0. E power 0 is 1. You substitute 1. That also will be periodicity. So it implies that you just divide the power, you divide by n. N by n will give you 1. Here you divide by n. So that will be e power 2 pi in by n. So alpha equal to, the multiplicative factor will be alpha equal to e power 2 pi in by n. Is it clear? You are going to divide This power divided by n, power divided by n will give you alpha equals e power 2 pi n by n. So compare e power I k a, that term will be I k a, I a gets cancelled. So k will be 2 pi n by capital N. So k will be 2 pi n by n a. Is it okay? Where n goes from 0 plus or minus 1. So if you substitute this value k here, then we will have psi of x plus a will equal n a will be e power 2 pi, and instead of k you can substitute 2 pi I n by n. A gets cancelled, correct? Here a gets cancelled. You have 2 pi I n by n psi of x. So this condition is Bloch theorem. So this condition is known as Bloch theorem. Psi of x plus a, which is equal to e power 2 pi I n by n. Actually e power I k a you have to substitute for, okay. Thus the solution of Schrodinger equation of a periodic potential will have the form of a plane wave modulated by the function having the periodicity of the lattice. The solution of Schrodinger equation of a periodic potential will have the form of a plane wave modulated by the function just now we discussed, having the periodicity of the lattice. So more explicit form for psi of x can be obtained by solving 2.08 earlier, which we have seen for psi of x. So that is your 2.108. Okay, psi of x plus a equal to e power I k a psi of x. So if I bring this term to this side, you will have psi of x equal to e power minus I k a psi of x plus a. So e power I k x psi of x equal to psi of x can be written as e power minus I k a psi of x plus a, correct? So put together that can be written as e power I k x plus a. So psi of x plus a. So joining together we will get psi of x equal to e power I k x u of x, where u of x plus a equal to u of x. So this is nothing but the periodicity. Okay, so periodicity multiplied by the plane wave equation, that will be the complete solution. So this is nothing but your Bloch wave function. So this is the conclusion. So this is known as Bloch function. We would like to mention that the solution of the free particle is being that exponential factor e power I k a and e power I k x. So exponential factor, while the periodic function can be said that it is a direct consequence of periodic potential. So since it's periodic potential, e power I k x exists, e power I k a also exists. So this is one of the major results for describing electrons in crystalline solids. Okay.